How to develop random forest ensembles with XGBoost. The XGBoost library provides an efficient implementation of gradient boosting that can be configured to train random forest ensembles. Random forest is a simpler algorithm than gradient boosting. The XGBoost library allows the models to be trained in a way that repurposes and harnesses the computational efficiencies implemented in the library for training random forest models. XGBoost API for random forest. The first step is to install the XGBoost library. I recommend using the pip package manager using the following command from the command line. Once installed, we can load the library and print the version in a Python script to confirm it was installed correctly. Running the script will load the XGBoost library and print the library version number. They are the XGBRF classifier and XGBRF regressor classes for classification and regression respectively. The number of trees used in the ensemble can be set via the n-estimators argument, and typically this is increased until no further improvement in performance is observed by the model. Often hundreds or thousands of trees are used. XGBoost does not have support for drawing a bootstrap sample for each decision tree. This is a limitation of the library. Instead, a subsample of the training dataset without replacement can be specified via the subsample argument as a percentage between 0.0 and 1.0, 100% of rows in the training dataset. Values of 0.8 or 0.9 are recommended to ensure that the dataset is large enough to train a skillful model, but different enough to introduce some diversity into the ensemble. The number of features used at each split point when training a model can be specified via the colsample binode argument and takes a percentage of the number of columns in the dataset from 0.0 to 1.0, 100% of input rows in the training dataset. If we had 20 input variables in our training dataset, and the heuristic for classification problems is the square root of the number of features, then this could be set to squar20, or about 4/20, or 0.2. XGBoost random forest for classification. In this section, we will look at developing an XGBoost random forest ensemble for a classification problem. First, we can use the make classification function to create a synthetic binary classification problem with 1,000 examples and 20 input features. Running the example creates the dataset and summarizes the shape of the input and output components. Next, we can evaluate an XGBoost random forest algorithm on this dataset. We will evaluate the model using repeated stratified k-fold cross-validation with 3 repeats and 10 folds. We will report the mean and standard deviation of the accuracy of the model across all repeats and folds. Running the example reports the mean and standard deviation accuracy of the model. Note, your results may vary given the stochastic nature of the algorithm or evaluation procedure, or differences in numerical precision. Consider running the example a few times and compare the average outcome. In this case, we can see the XGBoost random forest ensemble achieved a classification accuracy of about 89.1%. We can also use the XGBoost random forest model as a final model and make predictions for classification. First, the XGBoost random forest ensemble is fit on all available data. Then the predict function can be called to make predictions on new data. The example below demonstrates this on our binary classification dataset. Running the example fits the XGBoost random forest ensemble model on the entire dataset and is then used to make a prediction on a new row of data, as we might when using the model in an application. Now that we are familiar with using random forest for classification, let's look at the API for regression. XGBoost random forest for regression. In this section, we will look at developing an XGBoost random forest ensemble for a regression problem. First, we can use the make regression function to create a synthetic regression problem with 1,000 examples and 20 input features. Running the example creates the dataset and summarizes the shape of the input and output components. Next, we can evaluate an XGBoost random forest ensemble on this dataset. As we did with the last section, we will evaluate the model using repeated k-fold cross-validation with 3 repeats and 10 folds. We will report the mean absolute error MAE of the model across all repeats and folds. The scikit-learn library makes the MAE negative so that it is maximized instead of minimized. This means that larger negative MAE are better, and a perfect model has a MAE of 0. Running the example reports the mean and standard deviation MAE of the model. In this case, we can see the random forest ensemble with default hyperparameters achieves a MAE of about 108. We can also use the XGBoost random forest ensemble as a final model and make predictions for regression. First, the random forest ensemble is fit on all available data. Then, the predict function can be called to make predictions on new data. Running the example fits the XGBoost random forest ensemble model on the entire dataset and is then used to make a prediction on a new row of data, as we might when using the model in an application. Now that we are familiar with how to develop and evaluate XGBoost random forest ensembles, let's look at configuring the model. In this section, we will take a closer look at some of the hyperparameters you should consider tuning for the random forest ensemble and their effect on model performance. The number of trees is another key hyperparameter to configure for the XGBoost random forest. Typically, the number of trees is increased until the model performance stabilizes. Intuition might suggest that more trees will lead to overfitting, although this is not the case. Both bagging and random forest algorithms appear to be somewhat immune to overfitting the training dataset, given the stochastic nature of the learning algorithm. The number of trees can be set via the n estimators argument and defaults to 100. Running the example first reports the mean accuracy for each configured number of trees. Note, your results may vary given the stochastic nature of the algorithm or evaluation procedure, or differences in numerical precision. Consider running the example a few times and compare the average outcome. In this case, we can see that performance rises and stays flat after about 500 trees. Mean accuracy scores fluctuate across 500, 1,000, and 5,000 trees, and this may be statistical noise. The number of features that are randomly sampled for each split point is perhaps the most important feature to configure for random forest. It is set via the col sample binode argument, which takes a percentage of the number of input features from 0 to 1. The example below explores the effect of the number of features randomly selected at each split point on model accuracy. We will try values from 0.0 to 1.0 with an increment of 0.1, although we would expect values below 0.2 or 0.3 to result in good or best performance, given that this translates to about the square root of the number of input features, which is a common heuristic. In this case, we can see a general trend of decreasing average model performance as more input features are used by ensemble members. The results suggest that the recommended value of 0.2 would be a good choice in this case.